In this video, we'll take a look at SN2 mechanisms. So before we get into any specific reactions or the mechanisms, let's define what's going on in SN2. So first of all, in any SN2 reaction, the S stands for substitution, the N stands for nucleophilic, and the 2 means bimolecular, which this means that the reaction rate is characterized by 2 molecules. So 2 molecules will determine the reaction rate. Both of their concentrations influence the rate. So this is very important for SN2. Now, the general mechanism, we've already looked at stuff like this. It involves a nucleophile that attacks an electrophile with some good leaving group. I've marked X here. This can be a halide, can be a tosylate, it can be many things, and we'll explore some leaving group identities, but normally it's shown as Rx, so the nucleophile will come in at this electrophilic carbon, and then the leaving group will leave simultaneously, and this will create the carbon nucleophile bond with your leaving group with a negative charge. So this mechanism is concerted, which means that the bond breaking and forming occurs simultaneously. So this nucleophile that's creating this bond at this R group occurs at the same time while this leaving group is breaking a bond at that R group. That's what we mean by concerted. You may also hear this called as one step. This is what we mean by one step. It's the bonds are breaking and forming simultaneously. All right, the next thing to talk about is the transition state. A transition state in a general sense is a transient species in which bonds are breaking or forming. And they could be forming simultaneously, like is the case with SN2, but it's simply that some bond is breaking and some bond is forming at the transition state. And this will occur at a local maximum in an energy diagram, a reaction coordinate. And we'll take a look at a few examples like that. But here is what we mean when we say transition state. These are things that can't be observed directly, like you cannot isolate a transition state and then directly observe that, but what you see are indirect measurements through spectroscopic data to determine that that transition state occurs or does not occur. So now let's take a look at a specific example of an energy of a SN2 reaction in which a specific transition state forms. So here we have hydroxide and a methyl bromide. So our hydroxide is our nucleophile. This is going to attack the electrophilic carbon. The leaving group, bromine will leave, and we will get our methanol and bromide. So, but the transition state that we're referring to here is in which the carbon-oxygen bond is forming at the same time that the carbon-bromine bond is breaking. And we represent this by showing dotted lines between the bonds that are forming and that are breaking. So if we considered this carbon to have these being bonds, not partial bonds, between the oxygen and the carbon and the bromine, this would have 5 bonds, which we know that carbon can only have 4 bonds, so that's why we know that this is an extremely unstable state in which these bonds are partially existing. So you can think of it as this carbon-oxygen having like half bond character and the carbon-bromine bond having also half bond-like character. So here's the transition state that occurs for this type of example, and this is very important because it shows that the oxygen and the bromine need to be as far apart as possible, which makes sense since this oxygen has to approach this carbon. It'll be easiest for it to approach with the bromine out of the way. Because remember, these hydrogens are relatively small atoms compared to the bromine, so they don't impede the nucleophile from attacking that carbon as much as the bromine, which is why we get this orientation in the transition state. Last thing to mention is this double dagger here represents transition state. It is the abbreviation that is commonly used. So if you see this, just know that that means transition state. And we put it in brackets as well to indicate that it's not a isolatable intermediate or anything like that. It is a transient species that only exists temporarily to create the products. All right, let's take a look at this specific example where we take hydroxide ion, react that with methyl bromide, and we get methanol and bromide ion back. So what we're interested in is demonstrating the thermodynamics of this process, and we'll show that on an energy diagram. So what we see now is a general energy diagram where we have time or the reaction progress on the x-axis and energy on the y-axis. So how we start this process is we're going to have a point in energy in which the reactants are stabilized. So I'm going to call that spot here. And this is going to be our hydroxide ions plus our methyl bromide. Okay. Then there's going to be some activation energy, so some Hill requirement to get here. And this is going to be our transition state at this top of the hill, at that peak. And then we're going to immediately collapse down to the products. So I'm going to draw the products here first before we proceed any further. So this makes methanol and bromide ions. So now, like I've mentioned, this top of the hill is the transition state right here. Okay, what's that transition state going to look like is the point at which the OH bond is forming at this carbon, while at the same time the bromine is breaking off of that same carbon. So what I'm saying would be illustrated like this, where we have the carbon with the 3 hydrogens, like this. And then the bromine bond is breaking. That's what we show as this dotted line. And the oxygen carbon bond is forming. So here is our transition state that is occurring at the top of this hill. And like I mentioned, there's an energy requirement from the reactants to the transition state, and this is known as the activation energy, this difference here, and we call that EA. EA is the activation energy, and this is the energy required to initiate a new reaction. So to go from the reactants to the transition state, then the transition state is extremely unstable, and this will immediately collapse down to our products. It could also collapse back to the reactants, which is true, but in this case, the driving force is that these products are more stable, so it will predominantly proceed in the forward direction once we get to this transition state. So now notice this transition state has 5 bonds if you were to consider the carbon oxygen and carbon bromine dotted lines as bonds. So that's why this is extremely unstable, because these bonds, if you will, they have like half bond character because they're forming, this bond is forming at the same time this bond is breaking. So there's not really 5 bonds on that carbon. It's just to illustrate that the bond is being formed and broken at the same time. And the last thing to point out is our difference in energies of the reactants and the products, which is our change in enthalpy, or delta H. And in this case, delta H is less than 0 because the reactants energy is higher than the products. So our final state minus our initial state is going to be negative, which is telling us that this is an exothermic reaction. So now using this, you could be asked to illustrate the energy diagram for an SN2 type mechanism, and it's always going to be this energy diagram in which you create one hill, one transition state, and then the opposite ends are going to be your reactants and products for the SN2 mechanism. The next thing to talk about is kinetics. So kinetics in a general sense are features that are related to the rate of a reaction. That's what we mean by kinetics in a chemistry sense. So for SN2 specifically, the rate is determined by some rate constant multiplied by the concentration of the nucleophile times the concentration of the electrophile, in this case an alkyl halide like Rx. So remember that the brackets mean concentration, so this will be something reported in molarity or something along those lines, some concentration. And this shows that it's bimolecular since this rate is determined by both the nucleophile and the alkyl halide. We'll see in other reaction types that it doesn't necessarily have to be bimolecular like this. This is a unique feature to SN2 mechanisms. So now, as to be complete here, K is our rate constant, Nu is our nucleophile, some negatively charged atom, or just nucleophilic atom, and Rx is an alkyl halide, or the leaving group's identity can vary. It doesn't necessarily have to be a halide, but as a beginning example, I will just use halides and keep it consistent in that sense. All right, now there are specific stereochemical outcomes of SN2 in all major types of reactions that we'll look about in the substitution and elimination section here. And in SN2, the nature of the transition state causes an inversion of stereochemistry, which what we mean by that is the absolute configuration will invert. For instance, if it starts, your starting material starts as R and it undergoes an SN2 mechanism, the product will be S. And the reason we can visualize this, and here's a specific example. So if we look, we have a chiral center here at this carbon with the bromine that is out of the plane of the paper. It is a wedge. And so this looks like R because they have bromine, the ethyl group, and the methyl group are priority 1, 2, 3. That looks like R. The hydrogen is in the back, so it is R. And then our nucleophile is this methoxide group here. This can attack the bromine and replace it. So the transition state that occurs is something like this, where the bromine bond, the carbon-bromine bond is breaking at the same time the oxygen-bromine bond is forming. So what this is forcing is that the bromine and the oxygen are as far apart as possible, which puts the oxygen in the back. So when this transition state were to break down, we would get this final product in which the oxygen now is a dash, it is in the back. So then when we look at our absolute configuration, it has oxygen, ethyl group, methyl group. That still looks like R, but now the hydrogen is in the front, which makes it S. Now, this is important, but keep in mind that this is only critical if the starting material is chiral. So always take a look at your starting material, and if it is chiral, then you need to pay special attention to the stereochemical outcome of whatever mechanism that is most likely in those reaction conditions. But if it is achiral, then more than likely the stereochemical outcome will not matter because it's going to be achiral as a product as well. So just pay extra special attention if you see a chiral center in any of these reactions. Okay, next thing to talk about is the leaving group ability. And the general rule for determining what's a good leaving group or not so good leaving group is that weaker bases are always better leaving groups. They're always good leaving groups. So this may be difficult because now you need to memorize what's a good base or a strong acid or anything like that. But if you remember this relationship that I'm pointing out here, that acids and their conjugate base have a relationship, and that relationship is if you have a strong acid, then you have a weak conjugate base, or vice versa. If you have a strong base, then you have a weak conjugate acid. You can use this to determine the leaving group ability for any specific series of different leaving groups. So using that then, let's look at the acid strength of the halide series. So here we have HI. HI is hydroiodic acid. This is a stronger acid than HBr, hydrobromic acid, which is stronger still than HCl, and hydrofluoric HF. So the reason for this, we've talked about in the Bronsted-Lowry acid-base video, but there is a large difference in the size between the hydrogen and iodine, and the larger the size, the weaker the bond is. The larger the size difference, specifically, the weaker that bond is. So what that means is that that bond is weak, so it's more likely to function as an acid and donate that proton, the hydrogen atom here. So, since this is the acid strength, then we know that its conjugate base, the I-, Br-, and so on, would be the inverse relationship. So what I mean specifically is the iodine is a worse base than the bromine, which is worse still than chlorine and still than bromine, based on the inverse relationship between this acid strength and the conjugate base strength. So now using this and our initial rule that weaker bases are better leaving groups, we can then rate the leaving group ability as the inverse of the conjugate base strength. So since iodine is a weak base, it's a great leaving group, and bromine's a better base than iodine, so it's a worse leaving group, and so on down the line. So you can use this for any set of leaving groups, provided that you have the pKa values of their acids. So here, this one you just have to have memorized this list, but otherwise you may be given the pKa values of a particular set of acids, and then you can use this scheme to determine what is the best leaving group out of the list of possibilities that you may be given. All right, the last thing to talk about is all of these factors that promote SN2. We've talked about many of them already, but let's put it all together in one nice page. So the first factor is that you want small electrophiles. So what this means is that you have a less substituted electrophilic atom, so carbon most of the time, the more likely SN2 is to proceed. So what that means is a primary electrophile is more likely to proceed in SN2 than a secondary or a tertiary. So let's put that here. So primary is better than secondary, which is better still than tertiary for SN2 type mechanisms. Next is the small molecular nucleophile. So what this means is the smaller the entire molecule of the nucleophile, so the less substituted that is, the better that nucleophile will function. And this is due to sterics, and sterics are essentially the bulky nature of a molecule. If it is more sterically hindered, it means there are larger groups that are on that molecule that would prevent another molecule from getting close. So what we mean here as a specific example is something like OH minus is a much better nucleophile towards SN2 than like T-butoxide. Even though they both have an oxygen with a negative charge, T-butoxide has these methyl groups that prevent the oxygen from approaching the electrophile, but this OH group only has a hydrogen blocking it, which isn't a big deal. So sterically speaking, this OH is a much better nucleophile because the entire molecule is smaller. So remember, molecule is referring to this entire species that has the oxygen atom and the hydrogen atom bound together. That is the OH molecule. Same thing here, the oxygen, all of this whole entire species is a molecule, not the individual atoms. So next is large atomic nucleophiles. So here we mean the individual atom that is functioning as a nucleophile. If it is larger, then it is a better nucleophile. So for instance, phosphorus and sulfur are much better nucleophiles than their counterparts. So for instance, OH minus is a worse nucleophile than SH minus because sulfur is much larger of an atom, which makes it a worse base. So that makes it a better nucleophile. So in essence, if the actual atom that is acting as a nucleophile is larger, then that is going to be preferred for SN2 type mechanisms. And lastly, polar aprotic solvents are the best. And what this means, we know what polar means, right? There has to be a difference in dipoles. And the second part, the aprotic part, means that they cannot participate in hydrogen bonding. So that is something like acetone. This has an oxygen, so it has a dipole there between the carbon and the oxygen, but there's no OH, so it cannot undergo hydrogen bonding. Another example is DMSO. This has no oxygen, hydrogen, or sulfur hydrogen bond, so it cannot participate in hydrogen bonding. So this is polar aprotic solvents. Now, using this entire scheme, you can look at any reaction conditions and predict what if SN2 is going to be a likely pathway based on this entire collection. Next, we'll look at a type of question that talks about the reaction rate. So what will happen to the rate of the reaction under these various conditions? So here is our reaction. We have a primary alkyl halide reacting with methoxide in a polar aprotic solvent. This is definitely going to undergo SN2, and we'll get this product. So recall that SN2 is a rate that's determined by the rate constant times the nucleophile concentration times the alkyl halide's concentration. So both of those will influence the rate of the reaction. So now if we look at a specific situation, we're saying that we're going to increase the nucleophile's concentration, NaOCH3, sodium methoxide. So this is going to increase the rate. Whatever amount we increase the concentration of this, it will proportionally increase the rate of the SN2 reaction. Okay, what about if we increase the concentration of solvent, which is acetone? So this will have no effect because the solvent is already going to be in much higher concentration than everything else. And as we see from our reaction rate, it's not involved in the mechanism. It is only there to dissolve the salt of the sodium methoxide. And then lastly, we say decrease the alkyl halide. So this is a decrease the rate by whatever amount we decrease the concentration of the alkyl halide. Because remember, we have this rate constant, this rate of law, this rate situation equation. So Rx is a alkyl halide. We decrease the alkyl halide here, so we also decrease the rate proportionally. Okay, next we were asked which reaction will proceed more efficiently, and we're given two specific situations. Here we see them. We have A, which has a chlorine leaving group reacting with hydroxide, making this alcohol. And then we have B, has a bromine leaving group reacting with this alcohol. So recall that HCl is a weaker acid than HBr. So that means that chloride ion is a stronger conjugate base than the bromide ion, which then means that leaving group ability, bromine is better than chlorine. So if bromine's a better leaving group, it means that B here, this reaction is going to proceed much faster and more efficiently as the question asks. So this will be more efficient. All right, the last set of questions will tie all of this together to predict if SN2 is going to be a likely mechanism for a series of reactions. So first, let's look at our electrophile in A, question A. We have a primary electrophile here because it's only bound to one carbon, this one down here. And then we have a phosphorus, pH3. So phosphorus is a large atom, and this is a small molecule because it's only substituted by hydrogens, and this is a polar aprotic solvent. So by all accounts, from our list of factors that influence SN2 likelihood, all of them are being checked. So this is definitely going to be an SN2 mechanism, which would cause us to get this following product, in which the lone pair on the phosphorus will attack this carbon, the bromine will leave, and then we'll get this phosphorus with a positive charge plus the bromine with a negative charge. Okay, next question, look at B here. So we have a benzene now in this case, and a tertiary alkyl halide. This carbon is bound to the benzene and these two methyl groups. That makes it tertiary. This is a large atom and a small molecule, and this is a polar aprotic solvent. So that would all be very suggestive of SN2, these conditions, but the fact that this is tertiary, it will not be SN2. So tertiary Rx, no SN2 possible. Okay, next reaction. Here we see tertiary electrophile again. This carbon is bound to three methyl groups. Here we have a polar protic solvent. So that's not likely for SN2, which, there you go, tertiary, polar protic, this is not SN2. Okay, here we have another set of questions. So here we are asked about this primary electrophile here. So we have a primary electrophile bound to this fluorine, and we have a sodium methoxide. So this is a small molecule and a small atom. So small molecule is favoring of SN2, and this is a polar protic solvent. So this is, if it's going to undergo a reaction, it's probably going to be SN2. But let me say this. So fluorine is a horrible leaving group because remember, we looked at the acid strengths of HCl, HBr, etc. Hydrofluoric acid isn't considered a strong acid. It's a weak acid, which means that its conjugate base is stronger relative to the other halides, which makes it a terrible leaving group. So this is a really bad leaving group. So if it's anything, it's SN2, but it's more likely no reaction. So if you wanted to do this reaction and you simply replaced fluorine with bromine or iodine, this is probably going to proceed to make the SN2 product. Okay, moving on. Here we have a secondary alkyl halide. This carbon is bound to 2 carbons. And then we have a very large molecule, small atom and a large molecule, and this is polar protic solvent. So this is not going to be SN2. The secondary alkyl halide would make it possible to be SN2. This nucleophile is so large, though, the molecular nucleophile is so large, it won't undergo SN2. It's not possible. Okay, and our last one for this video. Here we have a primary electrophile. With this carbon is bound to just one other carbon and then the bromine. Here we have a small atom and a small molecule. So small molecule is indicative of SN2. And then this is polar aprotic acetone. So this is going to undergo SN2 primarily, and that will give you the alcohol, in which this negative charge attacks the carbon, kicks out the bromine. You get the alcohol plus the bromine, the NaBr, sodium bromide. So, all right, that is all I have for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel. If you have any questions, feel free to leave them down in the comment section below, and I'll get to them as soon as I can. So with that, I will see you all in the next video.